Hello, my name is Jürgen Schnack. Welcome to my presentation on results that we achieved at the Leibniz Supercomputing Center during the past years. I'm a physicist and I'm going to talk about certain quantum spin systems such as the kagome lattice antiferromagnet. This talk is available also on my webpage. I'd like to thank not only the Leibniz Supercomputing Center, but also the Deutsche Forschungsgemeinschaft for continuous support of this project and many other projects. Today, I'd like to talk about results obtained in quantum magnetism. Quantum magnetism is a field that might be not so familiar to you. It belongs to the realm of physics. And in quantum magnetism, we describe magnetic systems in terms of interacting magnetic moments. You may picture them as compass needles arranged, say, on a lattice and attached, say, to certain positions, and due to their interaction, they orient. And in physics, we know that these moments are described by angular momenta, for instance, by spins. And with effective models, we describe the magnetism of insulators, and we investigate whether there are non-trivial properties, new phases of matter, and so on. And I'd also like to point out that quantum magnetism forms the foundations of quantum computing, because quantum computing is expressed in terms of these quantum mechanical operators that we call spin. In this field, we describe a system by effective models that are expressed in terms of Hamiltonians, such as the Heisenberg Hamiltonian, given here by the first part of this Hamiltonian. The second part is the interaction with the external magnetic field, and it's called a Zeeman term. Let's focus on the Heisenberg model. In the Heisenberg model, two spins situated at sites I and j interact with a strength that's given by the prefactor here. And this prefactor can be ferromagnetic or antiferromagnetic. And in the kagome lattice antiferromagnet, in the way that is sketched here, neighboring spins interact with one and the same exchange interaction, capital J. And what you see here depicted in colors is a classical ground state of the kagome lattice antiferromagnet. But today we want to deal with quantum properties of this system. Well, quantum magnetism very, very soon yields huge mathematical problems. And the reason is that you express this Hamiltonian as a matrix. And the whole problem we have to solve is an eigenvalue problem of huge dimension. To give you an example, n spins lead to a Hilbert space dimension of 2 times s plus 1 to the power of n. So for, say, 42 spins of size 1/2, this yields a dimension of 4 times 10 to the 12. And nobody can diagonalize a matrix that is 10 to the 12 by 10 to the 12. Even when using symmetries, the exponential growth with the number of constituents renders an exact treatment of large systems impossible. But in order to predict or calculate thermodynamic properties such as specific heat or magnetization, we need to evaluate the partition function. And the question is, can we approximate the partition function by some means in order to obtain approximate thermodynamic properties? And the answer is yes, we can do that. Namely by means of trace estimators and in Krylov space representations. Well, a trace estimator, that is step 1, replaces a trace by an expectation value with respect to a random vector. And the random vector with respect to some orthonormal basis is in its simplest form given by random signs. So random values plus minus 1, and it's astonishingly accurate. And one can say the bigger the space, the more accurate is the trace estimator. The second step is to deal with this exponential. And this exponential is diagonalized in a Krylov space. The Krylov space arises from the random vector if you apply all the terms in a power series, say up to a certain order, to the random vector. This gives you linearly independent vectors that span the Krylov space. And if we diagonalize the Hamiltonian in that space, we obtain an approximate form of the partition function that includes or is given by the energy eigenvalues in the Krylov space, as well as weight factors that come from the overlap of the random vector with the eigenvectors in the Krylov space. And with that, we can evaluate approximations of observables. And you should realize at this point that I approximate a thermodynamic observable by just one random vector. And this is astonishing. And indeed, it works. It works better if you average over a number capital R of these random vectors. This approach is implemented in a freely available software called SpinPack, developed by Jörg Schulenburg, who works at the Computer Center Magdeburg, and it's MPI and OpenMP parallelized, and we used it so far on up to 3,000 nodes. To give you an impression of how accurate the method is, look here at the a spin ring as an example of 10 spins 5/2. The Hilbert space dimension is 60 million, and each single random vector gives one of the light blue curves here in the magnetization or heat capacity. And say above a certain temperature, that's already accurate with one random vector, okay? Below that temperature, we observe large variations, but when averaging, then given by the dots, the average approximation is exactly on top of the exact method that we can evaluate by use of group theory methods. For certain systems, such as the sawtooth chain here in this example, the accuracy is, even with a single vector, very good down to very small temperatures. And that is due to the fact that in these systems where we have competing interactions between spins, that in these systems, we observe frustration. We call these systems frustrated. And technically speaking, frustration works in your favor. Well, let me come to the physics of the kagome lattice antiferromagnet, because that's the reason why we do all these calculations. We want to understand how that system works, and that's not so easy for the kagome lattice. People call the kagome lattice antiferromagnet notoriously enigmatic, and that means it's very hard to get solid results on this system, and this not only concerns the ground state. We know or we believe, or we have strong hints that it is a spin liquid, but there are variants of spin liquids, and it's not clear yet which applies. And we also have no idea, or very little, on thermodynamic functions. People believe, from an analogy to classical physics, that there should be a macroscopic number of low-lying singlet below the first triplet, and they are expected to condense. We know already that the magnetization jumps to saturation. That can be proven and was done by us. The magnetization curve at 0 temperature also features plateaus, the question is how stable are they against thermal fluctuations? So if you increase the temperature, what's left over? And then another hypothesis concerns the crystallization of localized magnon below the saturation field, and I come to that in my talk. Well, here you see two graphs that we obtained in Garching, and they deal or show properties of the kagome lattice with 42 lattice sites. That was the system with Hilbert space dimension of 4 times 10 to the 12. But in this approach of the finite temperature Ransausch method, it's possible to go up to this size. And on the left-hand side, you see the heat capacity, and there's a major peak in the heat capacity that we understand. That's not so interesting. Interesting are these small peaks that appear for increasing system size, and with system size, this peak moves towards higher temperatures. And this is counterintuitive because this peak is given or results from the low-lying singlets, and if they would condense, we would expect the opposite direction, but this is not the case. The peak moves upwards, and it's believed, or there are numerical hints, that in the end it will end up as a shoulder, sorry, not that, but that big, as a shoulder on the low temperature side of the major hump. This is shown here in this paper. In our paper, given here, we also provide the magnetization curve that features here at 0 temperature this jump, and some of the here is a famous plateau at 1/3. But we are now able to investigate how the magnetization curve looks like for increasing temperature, and it's getting smooth rather quickly with temperature. Well, at very high fields close to the saturation field, here the saturation field is normalized to 1, at very high fields, we observe a plateau below the saturation field, and we know that on this plateau, we have so-called localized independent magnons on the kagome lattice. These are exact eigenstates, and the question is whether these localized states that are not allowed to touch each other in the ground state, because that would increase their energy. So we wonder whether they will be able to form a crystal as sketched here in this artist view, and whether one would be able to observe this crystallization, for instance, by observing a peak of the specific heat. You may know that phase transitions are accompanied by peaks of thermodynamic functions. For instance, here we observe this peak, and this peak is indeed related to the crystallization of magnons below the saturation field. We can prove this by analogy to a model that is called the hard hexagon model, and a third model that's called the loop gas model. And if you're interested, then just please have a look here at this physical review letter, where we could publish these exciting results. And we are also able to provide a phase diagram, namely as a function of the magnetic field, to tell you at which temperature the transition occurs. And this is experimentally relevant, and was also a good motivation for our studies, because there are materials such as this cadmium capelasite that show properties very close to what we calculate in the idealized model. Well, with that, I'm coming to the end. I'd like to thank the Leibniz Supercomputing Center for continuous support, which made these world record calculations possible that I showed you today. And I'd like to thank you for your attention. And I'd like to close by showing my collaborators, Andreas Honecker, Johannes Richter, and Jörg Schulenburg, with whom I work for a long time on these exciting problems of quantum magnetism. Thank you.